we have learned already that enolates are important reactive intermediates. When an enolate reacts with an alkyl halide, a substitution reaction can take place. Of course, enolates are nucleophilic, therefore they can react with all kinds of electrophiles. If the electrophile is an alkyl halide, substitution reaction can take place. If the electrophile is an aldehyde or a ketone, nucleophilic addition type can take place. That's typically an aldol reaction. If the electrophile is a carboxylic acid derivative, such as an acid halide, acid anhydride, or an ester, that's typically glycine. The product, obviously, of an aldol reaction is beta-hydroxy carbonyl compound, which can undergo elimination if the beta-hydroxy carbonyl compound is treated with a base or an acid. The product of the glycine reaction is the 1,3-dicarbonyl compound. Now, alkyl halides, aldehydes and ketones and carboxylic acid derivatives are not the only organic electrophiles. It is possible to have alpha-beta and saturated carbonyl compounds as electrophiles. In other words, what if an enolate reacts with an alpha-beta and saturated carbonyl compound? What product do we obtain, or should we obtain? Let's draw a general scheme for the reaction. We begin with a general ketone of this type, a ketone with an alpha hydrogen or a hydrogen on the alpha position, and of course we recall the pKa value for that acidic position, or for that carbon. pK is about 24 ketones in general, so we can write that down. pK is about 20 for hydrogens on this alpha position and this general structure of a ketone. Now, if ketones are treated with a strong base such as LDA or an amide in general, then the amide or LDA can convert the ketone quantitatively into the corresponding enolate. So if the aldehyde, if the ketone or the carbonyl compound in general is treated with LDA, for example, then the corresponding enolate is obtained quantitatively because LDA is a very strong base. You can recall the pKa of the conjugate acid of LDA, diisopropylamine. pKa is 38 or 40, something like that. And of course, pKa for ketones is about 20. Of course, the stronger acid, which is the ketone, should react with the stronger conjugate base that comes from the weaker acid. So this reaction is likely, and that's why LDA is capable enough to convert ketones or carbonyl compounds completely or quantitatively into the corresponding enolates. At this stage, having reached this reactive intermediate or versatile reactive intermediate, this can be reacted with all kinds of electrophiles now. We've seen before reactions of enolates with alkyl halides. We've seen reactions of enolates with aldehydes and ketones. We've seen reactions of enolates with carboxylic acid derivatives. What if now, and that's really the point of this discussion, what if an enolate is reacted this time with an alpha-beta and saturated carbonyl compound? So if this enolate is treated with an alpha-beta and saturated carbonyl compound, something like that, and of course it is alpha-beta and saturated, there is a double bond between the alpha and the beta carbons. Now, the enolate, if you recall the enolate again, if the enolate is reacted with an alkyl halide, it does SN2 type reaction. If the enolate reacts with an aldehyde or a ketone, the enolate therefore is capable of a nucleophilic addition. If an enolate reacts with a carboxylic acid derivative, then nucleophilic acyl substitution takes place. Therefore, the enolate is capable of doing so. Now, if the electrophile is an alpha-beta and saturated carbonyl compound, the enolate can do what's called 1,4 addition or conjugate addition at the, or attack, nucleophilic attack at the beta carbon. And of course, we learned before that that position is electrophilic, and that's proven by resonance. So the enolate can attack the beta carbon of an alpha beta unsaturated carbonyl compound in 1,4 addition. Remember, double bond, single bond, double bond. This is a conjugate system. This reaction is called conjugate addition. It's called 1,4 addition also because you can number them actually. 1, 2, 3, 4. You can put 1, 2, 3, 4. So that's why this reaction is called 1,4 addition. It's called also conjugate addition as opposed to 1,2 addition or direct addition. The bond in this case will be between that alpha carbon of a ketone and the beta carbon of the electrophile or the alpha beta unsaturated carbonyl compound. The intermediate that's obtained is actually this, where a bond is formed between the alpha carbon. So that alpha carbon is this one that comes from the original carbonyl compound, a ketone in this case. And of course, this position is the beta carbon from the alpha beta unsaturated carbonyl compound. So what's obtained now is actually an intermediate enolate which can then undergo protonation to give finally 1,5 dicarbonyl compound. Remember, that's the alpha carbon again. That's of course the beta carbon from the alpha beta unsaturated carbonyl compound. If you number these carbons, you will see it is 1, 2, 3, 4, 5. It's a 1,5 dicarbonyl compound or a 1,5 diketone specifically. In this case, of course, this is an enolate intermediate. This is an enolate, but the enolate gets protonated if it's treated with the hydronium ion to give eventually the ketone. This structural unit is very, very important, and it's very characteristic of this conjugate addition of an enolate with an alpha beta unsaturated carbonyl compound. The reaction is named as Michael addition. So Michael addition, therefore, is a reaction between an enolate from a carbonyl compound with an alpha beta unsaturated carbonyl compound. So that's alpha beta unsaturated carbonyl compound being the special electrophile in this case, which makes this reaction very distinct from other reactions of enolates. So in summary of this reaction, Michael addition is a reaction between an enolate and an alpha beta unsaturated carbonyl compound. The reaction type is 1,4 addition or conjugate addition. The product is 1,5 dicarbonyl compound.